Welcome to lesson 8.5. It builds an idea we've already seen. This red line that you're looking at is going in the direction 2, 3. You can see it goes 2 on the x, 3 on the y. And if we use 2, 3, if we put the 2 and 3 in front of x and y, as you see over here, it acts as the normal to the blue line, so that red line is perpendicular to that blue line. And that blue line is the set of all points that start at the origin and go perpendicular to the vector 2, 3. That takes you to all those points. Now, when you go perpendicular in 2D, there is only one direction that works. But now we have a line in 3D. You can see it's got changing x, changing y, and changing z. And I want to go perpendicular to that line, but in 3D. So that blue line is perpendicular to that red line. You can see it best in that angle. In 3D, they form a 90-degree angle. But that's not the only way to form a 90-degree angle with that red line. Here's another line that forms a 90-degree angle with that red line. And you can see I can make them line up like that. But that green line is perpendicular to that red line. If you rotated the blue line, you could make it land on the green line, and they would stay perpendicular to the red line. And I can add another line, and that one is also perpendicular to the red line. You can see that there. All three of those lines are perpendicular to the red line. And here's another one, and here's another one. All of those lines are perpendicular to the red line. How many lines go through the origin and are perpendicular to that red line? Well, there's an infinite number, because there are an infinite number of directions that are perpendicular to that red line. There's a whole circle of directions that are perpendicular to that red line. And if I took them all, if I took all those directions, I would get a plane. That red surface is a plane that is perpendicular to that red line. And you can see all those lines lie in the plane. And there are an infinite number of other lines that go through the origin and are perpendicular to that red line. So that red line is a normal. It is perpendicular to a plane. In 2D, a normal defines a line. That red line is a normal, and that in 2D, the blue line is defined by that normal. In 3D, that red line is a normal, and it is normal to the plane. So a normal defines a line in 2D, it defines a plane in 3D. So let's look at what kind of calculations we would do here. The Cartesian equation of a plane. I've drawn the point 1, 2, 2, and the normal -1, 2, 6. And I've only drawn a line that is perpendicular to it. But there is a plane. You could go this way perpendicular, or you could go out of the page and be perpendicular. Picture rotating this around in a circle and forming a plane. So take your point Q and say that it's on the plane, and let's find the vector AQ. Well, AQ is Q minus A, is x minus 1, y minus 2, z minus 2. And I want AQ to be perpendicular to the normal, so I want that dot product to be 0. So I want -1 times x minus 1 plus 2 times y minus 2 plus 6 times z minus 2 to be 0. And I'll expand that. And then I'm going to collect like terms. And that's what we call the scalar or Cartesian equation of a plane. And this works just like a line, that this -1 and this 2 and this 6 come from the normal. So that equation tells you that this plane is perpendicular to the vector -1, 2, 6. And this brings us to the last piece of the the last piece of the unit. The Cartesian equation of a plane is ax plus by plus cz equals 0 with normal ABC. So if I see the plane 3x plus 4y minus z plus 7 equals 0, for example, then I know the normal, the vector perpendicular to that, is 3x plus 4, nope, sorry, the normal is 3 comma 4 comma -1. And that is the last thing you need to know for this term for your test. That the scalar equation of a plane looks just like the scalar equation of a line, but you're in 3D. So those are the 4 things you need to know for this test. So what kind of questions? Well, last class we found the vector equation of a plane that goes through 3 points. Now we'll find the Cartesian equation. We need a starting point. Let's choose A. And we need 2 direction vectors. Well, I'm going to choose AB and AC. I'm going to choose the vector that connects A to B and A to C. That'll make my plane. That's B minus A. That's C minus A. I'm subtracting, doing my very best. Okay. So that information defines a plane. But for a scalar equation, I need a normal. I need a vector that is perpendicular to both of those. So picture the vector that comes up out of the page here. It's perpendicular to AB, and it's perpendicular to AC. That's the normal to the plane. And we know from Unit 7 that if I need a vector perpendicular to 2 vectors, I cross them, because the cross product always goes perpendicular to the 2 vectors you made. So I get 0 minus 5, copy the x values. I get 1 minus 4, and I get -20 minus 0. I get -5, -4, -20. And that's the normal vector. And because it's the normal vector, I know the equation of this plane is -5x minus 4y minus 20z plus d equals 0. The normal vector gives me the coefficients for the equation, the scalar equation. And now how do I get d? Well, I'm going to plug in my point. I'm going to plug in a. X is -1, y is 2, z is 5. I'll solve for d. 5 minus 8, -3, I got -103, plus d equals 0. I got d equals 103. The answer to this question is -5x minus 4y minus 20z plus 103 equals 0. That is the Cartesian equation of the plane. It shows you the normal. And the 103 doesn't show you much by itself, but it makes sure that it hits this point. If I have extra time or something, I could plug in another point or another point and make sure it works as well.